7 from exercise 10.2. We are given two concentric circles. Two concentric circles. I'll draw the diagram first. Of radii 5 centimeters and 3 centimeters. Hope this appears like a circle. Let me take this as 3 centimeters and this radii as 5 centimeters. 5 centimeters. Now it says the length of the chord or the chord on the bigger circle touches the smaller circle. Length of the chord, you have to find out the length of the chord. Length of the chord that touches the smaller circle. You have to find out the length of the chord that touches the smaller. Now this is the chord that is touching the smaller circle, and the chord is drawn on bigger circle. So let's solve this question. Now this you know already that is 5 centimeters. So let me write like this. R is for smaller circle, so I'll write with yellow chalk. R is 3 centimeters, and since white is bigger circle, I'll write R 5 centimeters. You have to find out this length. Let me indicate some letters here. A and B. It is find length AB. The question is find length AB. Find length AB. What I'll do is I'll join the endpoints of the chord with the center. Let me see what happens. This is the center. I am joining the endpoints of the chord to the center. Now I know that this is still 3. If I indicate this by letter O and this by say C, OC is 3 centimeters. How? OC is still the radius of a smaller circle. Radius of a small circle. And AO or OA is radius of bigger circle. Let me write in yellow chalk for smaller circle. So therefore OC is 3 centimeters and this is OC 3 centimeters, and OA is 5 centimeters. I've written here R for bigger circle. R, that is radius for the bigger circle, drawn in white chalk, is 5 centimeters. So this is 5 centimeters. Now again from theorem 10.1, angle ACO is 90 degrees. The tangent and the radius, the length of the radius or the line from center O onto the tangent at the point C on the circle are at right angles. These two lines are at right angles from theorem 10.1. So I can apply Pythagoras theorem to triangle ACO from triangle ACO. You have hypotenuse square is equal to base square plus perpendicular square. Now this is at right angles, you gotta mind it. So therefore OA square is equal to base square, that is this is the base, OC square plus again you have AC square. Am I right? AC square. OA square is 5 square. OC square is 3 square. I've written here the values already. This is plus, AC square is unknown. So 5 square is 25 and 3 square is 9. Square is 9 plus AC square. 25 minus 9 is 16. Therefore, AC square is equal to 16, or AC is equal to plus or minus 4. AC is equal to plus or minus 4, but that's not the end of the solution here. I have to find out length of the AB. See, this is the question. Find length of the AB. Therefore, AB is nothing but AC plus BC or AC plus CB. AC is found out. Since length cannot be in negative term, if length is not a negative term, so you take AC is equal to 4 centimeters. Similarly, in triangle OCB is at right angle. This is a right angle. OCB is a right angle. So therefore, I can apply Pythagoras theorem from triangle OCB. I have OB square is equal to, then you have OC square plus BC square or CB square, right? That is OC square plus CB square. OC is again radius of the smaller circle, which is 3 centimeters, is equal to 3 square. OB is again radius of bigger circle, drawing white chalk, which is 5 centimeters. 5 centimeters square. This is plus CB square. 5 square is 25. Again, you have 25 minus 9 is equal to CB square. Therefore, CB is equal to again plus or minus 4. Or CB is just plus 4 centimeters. So I substitute the values of AC and CB in this equation. I'll get length AB. AC is also 4 and CB is also 4. Therefore, AB is equal to 8 centimeters. AB is equal to 8 centimeters. I'll repeat the problem here again. There are two concentric circles. Concentric means circles with same centers. These two circles having same center, centered at O, having radii 5 centimeters and 3 centimeters. And we are given a chord, we do not know the length. So this is the chord AB, and we have to find out the length of the chord. I have indicated the chord by AB. AB is chord, and we join point A and O, again point B and O here, and I have applied Pythagoras theorem to these two triangles, and I found out what is length of AB. 3 steps involved here. Draw the diagram correctly and neatly, and then from the theorem 10.1 you say that this angle is at right angles. Apply the Pythagoras theorem in the third step and get the answer. And now the next question I'm about to solve is pretty interesting question, and there are 2 ways to solve it. That is question number 8. I'll write the question for you guys, since it's a small question. A quadrilateral ABCD is drawn to circumscribe a circle prove that AB plus CD is equal to AD plus BC. We have to prove that AB plus CD is equal to AD plus BC. A quadrilateral ABC is drawn to circumscribe a circle. That is, circle is exactly touching the periphery of quadrilateral. This is what it means. The statement means that the quadrilateral is exactly touching the periphery of circle or vice versa. It means the same. Let me draw a quadrilateral here and then circle. Let me write the letters now here. Say A, B, C, D. So this is a quadrilateral. A, B, C, D is a quadrilateral, and there is circle within the quadrilateral, and you have to prove that AB plus CD is equal to AD plus BC. AD plus BC. Let me indicate by this point as P, Q, R, and this. Now this can be solved like this. You straight away write here as the answer AB plus CD is equal to AD plus BC. AB is nothing but AP plus BP. So I'll write so that you can see it. AB, I am writing the result first, and what am I doing here is I am backtracking the solution. I am solving it in the reverse order. First I am taking the result here and then going back steps. I am taking the steps backwards. AB plus CD is equal to AD plus BC. AB is equal to AP plus PB. AB is equal to AP plus PB. So AP plus PB plus CD is nothing but CR plus RD. CD is equal to CR plus RD. So CD is equal to CR plus RD. This is equal to AD is nothing but AS plus SD. AS plus SD plus BC is BQ plus QC. BQ plus QC. Now the thing is, we have to show in the answer that how did we do this, right? Without doing this, okay. How does this equation come? That's the question. It comes like from here. If you write, we know that tangents drawn from an external point to the circle are equal in length. So let me write all those equations. So starting from here, AP is equal to AS, AP is equal to AS, and here BP is equal to BQ, BP is equal to BQ. Since why am I equating these two lengths? That is because this form tangent to the circle. This is external point. At this point, we can have two tangents drawn to the circle. So that will be equal in length from the theorem 10.2. At point C, you have CQ is equal to CR. And at point D, you have DS is equal to DR. What do you have here? AP plus BP and CR plus RD. Can't I write this equation as DR or RD? It means one and same. Please mind it. So DR is equal to DS. I'd like to have this in the reverse order. That is because for the sake of convenience, I want AB plus BP, AB plus BP or PB in the left hand side, and then CR plus RD, CR plus RD again in the left hand side. So therefore, I also write this equation as CR in the reverse order. CR is equal to CQ. Right? I've just reversed. It means one and same. So equation 1, equation 2, and then you have equation 3, equation 4. Now adding equation 1, 2, 3, 4, you get this equation, and you straight away you have this. Let me write that. Now add equations 1 to 4. So let me write AP plus PB or AP plus BP. It means same. AP plus, since I've written PB here, let me take BP as PB. AP plus PB plus I'm adding 1, 2, 3, 4. That is DR plus CR, or CR plus DR is also RD. So therefore I'll write CR plus RD is equal to, I'm adding the right hand side now, AS plus BQ, AS plus BQ, AS plus BQ plus you have DS plus CQ, you have DS plus CQ. Now rearranging the terms, I have AP plus PB. If you solve in this method, there is no room for error. Mind this, guys, please. Just straight away write the result here and split the length AB in terms of two smaller lengths from the figure. AB is split into two smaller lengths, that is AB plus PB. I can take a straight away right here. Again, then I've done for same for all the other three terms. Plus CR plus RD. I'm taking AS and SD together, or AS and DS or SD. AS plus SD together, plus you have BQ plus QC. BQ plus QC. We have BQ plus QC. From the figure, let us see what is sum of AP and PB. Sum of AP and PB is AB plus sum of CR plus RD. CR plus RD, isn't it CD? CR plus RD is CD, is equal to AS plus SD. AS plus SD is AD. Then BQ plus QC. BQ plus QC is BC. Now in the examination, you might want to erase this, or you can just, if you have written it in the pencil, you can erase it, or if you have written it with a pen, you can strike it off. This is one of the methods. Another method was just write first these equations and add all the equations here. Add and just simplify and adjust the equations to get AB plus CD is equal to AD plus BC as your proof. I'll repeat this again. I started from here. I straight away took the result of the problem and kept it here, and I've split the result AP plus PB, and plus CD was split into CR plus RD from the figure, and AD was split into AS plus SD, and then you similarly you have BC written as BQ plus QC. Now what I have done is, the question was, how did you prove this? How did you write this? That's the question. What do you do? From theorem 10.2, you write the lengths of the tangent drawn from a point external to the circle are equal in length. So you write that AS is equal to AP, you will get 4 equations. There are 4 points and you get 4 equations, because at one point you will have exactly one equation. So you will have 4 equations, and add those 4 equations, right hand side separately, left hand side separately, and adjust the equation to get the result. AB plus CD is equal to AD plus BC. This is a pretty simple problem if you do it in this method. I prefer solving this problem in this method because this might be confusing at later point of time, where to take when and where to do what.
No more spending your energy and money on coaching classes or missing classes for rain, for rally and any other nonsense. Subjects covered by multiple teachers with repeat telecasts. Doubts, concepts, applications, no problem. All explained through great and significant animation. So sit back comfortably in your home and watch Study Spectrum TV channel.
Problem number 9. This is given in the textbook. The diagram is given. Draw the diagram. Let me write the same letters here. This is X, this is Y, X, this is Y, this is O, right, and this is letter Q, B, E, A, B, Q, A, B, and to prove that AOB is 90 degrees. To prove that angle AOB is 90 degrees. So what we'll do is start solution now. Solution. Join O to this point, dotted line, and mark this point with letter C. Now, I see two quadrilaterals here, first of all, and let me take this point as P. OPAC, OPACO is one quadrilateral, and OQBCO is another quadrilateral. We have to prove that angle AOB is equal to 90 degrees. Angle AOB is 90 degrees. So what we'll consider here is, we'll consider quadrilateral here, one of the quadrilaterals, and we'll consider straight line POQ, and we'll use the angle summation, that is angle summation, that is sum of angles on a straight line is 180 degrees. We'll use that concept and prove that AOB is 90 degrees. In quadrilateral, okay. Now since OP and OC are radii in a circle, they will be of equal length. OP is equal to OC. Radius, I'll write in the bracket, since they are radii. Since OA is common to both the triangles. Now there are two triangles within a quadrilateral. Within a quadrilateral OCAPO, there are two triangles OPA and OCA. OP from the triangle OPA is equal to OC from the triangle OCA. I have written here. Similarly, OA is equal to OA again here. OA from the triangle OPA is equal to OA from the triangle OCA. OA is equal to OA common side. That is because of common side they are equal. And now what is remaining? Radius is done, OC is done, and then common side is also done. The remaining is tangents drawn to the circle from a point external to the circle. Point A is external to the circle, and there are two tangents drawn like this. So shouldn't they be equal? Yes, from theorem 10.2 you have tangents drawn from a point external to the circle are of equal lengths. So I'll write PA is equal to CA from theorem 10.2. Or you can write in bracket that tangents from a point external to the circle are equal in length. Now since all the sides of the corresponding sides in these two triangles are equal, therefore I conclude from SSS criterion that these two triangles are congruent. Triangle, say OPA, and triangle OCA are congruent. Triangle OPA and triangle OCA, this one triangle and this another triangle, they are congruent. Similarly, I'll take now in quadrilateral OQBCO, I have two triangles OQB and OCB. This is from, I'll write here for you guys, from triangle OPA, triangles OPA and OCA. I have proved that they are congruent. So what else can I write from this proof? I can also write that corresponding angles should be equal. So therefore I conclude POA, angle POA is equal to, I have proved that triangle OPA and triangle OCA are congruent, so I write, therefore the corresponding angles will also be equal in the two triangles. So therefore angle OPA is equal to angle OCA. Angle OPA is equal to angle OCA. Now from the quadrilateral OQBCO, I have two triangles. Triangle OQB, so I'll write here. From the triangles OQB and OCB, from those two triangles I have OQ is equal to OC, because OQ and OC are radii of the circle. See, this is the diameter PQ, and QO or OQ and OC are radii. So I write OQ is equal to OC. This is radii. Similarly, OB is a side common to both the triangles, so it will be of equal length in both the cases. So you will have OB is equal to OB common side. OB is equal to OB, and what is left out? This point. This side is left out. I have covered radius and I have covered the common side. This side is left out. This side will also be equal in corresponding triangles. That is, QB will be equal to BC, because from point B we have drawn, apparently there are two tangents here from point B, BQ and BC. So therefore BQ is equal to BC. BQ is equal to BC. This is from theorem. So from SSS criterion, I conclude that triangle OQB and triangle OCB are congruent. So therefore, can I write angle OQB? That is, now see, the corresponding angles are equal. So therefore, what am I writing now? And what am I going to write now is triangle. Angle angle QOB will be equal to BOC. Angle QOB equal to angle BOC. That is corresponding angles. Now, when I say corresponding angles, it means that, see, this way the triangles like this. Now these two form corresponding angles. These two angles will form corresponding angles. These two angles will form corresponding angles in these two triangles. Similarly, you have these two angles equal. Why am I writing only these two angles? Why am I not writing the other angles? Because I don't want other angles. Because what I said in the first place, I said I'm going to use the property of summation of all the angles on a straight line will be equal to 180 degree. The sum of all the angles on a straight line will be equal to 180 degree. I'm going to use that. Therefore, I'm trying to find out all these angles. I'm trying to find out those angles so that I'll add those and equate to 180 degree and see whether it will get AOB is equal to 90 degrees. So next point. So this is from, since they are congruent, I've written this. POQ is a straight line. So therefore, angles made by any line onto it will be, sum of the angles made by the lines onto it will be equal to 180 degrees. Therefore, I am going to write now POA plus angle POA plus angle AOC plus angle COB plus, so what is this? Angle POA, okay. Angle COB equal to angle QOB. Okay. Therefore, this is QOB next. Angle QOB is equal to 180 degrees. Sum of all the angles, angle POA plus angle AOC plus angle COB plus angle BOQ will be equal to 180 degrees. That is angle 1 plus angle 2 plus angle 3 plus angle 4. Now 1 is equal to angle 2. I have proved that these two triangles are congruent. So in place of POA, I can write angle AOC. So that gives me 2 times AOC. 2 times angles AOC. I hope you're understanding. See what have I done here? I've proved that triangle APO and triangle ACO are congruent. So therefore the corresponding angles will be equal. Now in this case, this is the case. If I am drawing separately, these are the two angles I am considering to be equal angles because they form corresponding angles in these two triangles. So this is P and here is A and you have got AO here. Just writing separately here. A, C. These two angles will be equal. POA, angle POA equal to, is as good as just separating these two triangles from a quadrilateral. Angle POA is equal to angle AOC. Angle AOC, I can write this. So that's what I've done here. Angle POA is equal to angle AOC. Therefore, when I substitute, let me just substitute here. Angle AOC plus this angle AOC written as it is plus. Now look at this. Angle QOB, by now you should write this. Angle QOB equal to what? If you got this as BOC, then you are right. Angle QOB now will be written as that is in place of QOB we'll write COB. Angle QOB will be equal to angle COB. Angle 3 is equal to angle 4 in other terms. So therefore I'll just place this as it is. This whole sum is equal to 180 degrees. 2 times AOC plus 2 times COB equal to 180 degrees. I've taken 2 common. AOC plus angle COB is equal to 180. Or angle AOC plus angle COB is equal to 180 degrees divided by 2, or angle AOC plus angle COB is equal to half of 180 is 90 degrees. But this is not the proof yet. What did we have to prove? We had to prove which angle is equal to 90 degree? Angle AOB is 90 degree. Angle AOB. Now may I write angle here, angle AOB as angle AOB, you can write in any other form, in this form also. Angle AOB is equal to angle AOC plus angle BOC, angle BOC. So therefore, or COB, it means same, one and same. COB or BOC doesn't make much difference. But where the angle is at which point, that is important. So therefore, this entire sum sums to angle AOB. Since AOB is equal to sum of those 2 angles, I write the sum of these 2 angles as AOB, which is equal to 90 degrees. Hence, we proved that angle AOB is 90 degrees. So this is, now I'll just erase this. Now given in the examination, if this kind of problem is given, say only this part is given, let us say this is general proof, right? This is not one particular problem, this is general case, which means that, right, when you have tangents drawn from external points in this fashion, numerical questions may be asked. Right? Now it is understood that this angle is 90 degrees straight away. Always. Right? I have proved it. So you might be asked angles, like you might be asked this angle, what is that angle? You can understand it, right? You can find out by finding out the opposite angle, this angle, and you can solve the question based on that. We are solving problems on circles from exercise 10.2. We'll solve problem 10 and 12 and we'll wind up this chapter. Question number 10 first. This is again a proof type problem wherein you have to prove something. I'll draw the diagram and I'll try to simplify the statement in terms of mathematical data. There is a circle given and you have to prove that now angle subtended by the tangent from a point external and angle formed by the radius at this point, that is this angle and this angle are supplementary angles. In easier words, these 2 angles are, when we add to these 2 angles we should get 180 degrees. Let me indicate by center O and say point P, which is external to the circle. Let me indicate this point as T1 and this point as T2. This is again very easy problem. We know that sum of all the angles in equilateral is 360 degrees. Let me write that first. From quadrilateral PT1O T2P, PT1O T2P, angle T1P, angle T1P T2 plus, I have considered this angle first, now I am considering this angle P T2O, P T2O plus angle T2O T1, angle T2O T1 plus angle O T1P, angle O T1P, O T1P. How many angles? 4 angles. Angle, say this is 1, say this is 2, say this is 3, and say this is angle 4. I am indicated by numbers now. It becomes easier that way. T1 P T2 angle 1 plus P T2O, P T2O is angle 3 plus T2O T1, T2O T1 is angle 4. Now this sum is equal to 360 degrees. O T1P, O T1P is angle T1P T2 is angle 2. So this is angle 2 and that is angle 1. This is equal to 360 degrees. Now this angle is 90 degrees. Angle 1 is equal to 90 degrees and also angle 2 is 90 degrees. Why so? That is from the theorem, line from center to the tangent is at right angles to the tangent. From the theorem 10.2, angle 1 and angle 2 is 90 degrees. So by substituting the values here, degrees, angle 3 plus angle 4. Now angle 1 and angle 3, angle 1 and angle 3 is 90 degrees, 1 and angle 3. So therefore angle 2 plus angle 4 remains here, angle 2 plus angle 4, right? What do I have to prove? That angle T1O T2 and angle T1P T2 are supplementary angles, or sum of angle T1P, this is TP, that is 2 groups, sum of angle T1P T2 and sum of T1O T2, T1O T2 is equal to 1. They are supplementary angles. So angle 2 plus angle 4 plus 90 plus 90 degrees is 180 degrees. That is angle that is 180 degrees. Just write here. Is equal to 360 degrees. 360 degrees. Therefore, angle 2 plus angle 4 is equal to 360 minus 180 degrees, which is equal to 180 degrees. Angle 2 plus angle 4 is 180 degrees. Now, sum of angle 2 plus 4 is as good as sum of these two angles. So I write, because this angle is equal to 2 and this angle is equal to 4. So angle T1P T2 plus angle T1O T2. That is the answer for the problem number 10. This is a proof type problem wherein you have to prove that The sum of the two opposite angles in case of a quadrilateral is 180 degrees, or these two angles or angles opposite in a quadrilateral are supplementary pair. When I say supplementary, it means that some of the angles should turn out to be 180 degree. Right. So what do we have here? That's it. Pretty simple problem.